All right, we're back, and this video is pretty straightforward. Just talking about this concept called relative abundance, which is basically how common isotopes are. Like if I were to dig in the ground and dig up some sulfur, dig up some carbon, dig up some gold, whatever it is, basically figuring out like, hey, what percentage of those atoms are a particular isotope? Okay, this explains, you might say, why do we care about this? Like, what's the big deal? Well, it explains why in the periodic table, right? If I pick any element, so let's say I pick aluminum, right? Aluminum has 13 protons. It has to have 13 protons. If it doesn't have 13 protons, it's not aluminum. Give it a proton, it's silicon. Take away a proton, it is magnesium, right? It has to have 13 protons. That's the atomic number, and it cannot change. If it changes, it's a completely different substance. Okay, and just for the record, just so you're aware, we can change protons. There's a way to do it. Very expensive, very challenging, and basically it's something we never do. Okay, could you turn something into gold? The answer is you can. It's just not worth it because it takes more money to do it than it does to get from the gold. Okay, so if you're like, hey, we figured out a way to make gold, yeah, but it's not worth it. Not yet at least. Maybe one day will be, but not right now. Okay, but what we can change, or what we do see change pretty commonly in nature, are the number of neutrons. Okay, and if you notice, right, the atomic number is always an integer. Right, hydrogen's always 1, helium's always 2, gold is always 79. Right, it's always an integer. It's never decimal. Notice though that the atomic mass on the periodic table is a decimal. Okay, and that is because of this relative abundancy thing I'm talking about. This idea that not every atom of gold has a mass of 196. Right? If I look at the mass of gold, it says the average is 196.97. Okay, that probably means, if you're saying what is the mass of it, it's probably 197. You might say it's not 197, it's 196, because this is a weighted average. Okay, it's very close to 197. It's probably the case that most gold atoms have a mass of 197. If you ask me how much, well, I need to give you some numbers for that. I don't expect you to memorize this stuff. That would be insane. Okay, a better example I can give you that's maybe a little bit easier to understand would be like carbon. Carbon's mass is very close to 12, because guess what? Almost all of carbon is carbon-12. 6 protons, and therefore 6 neutrons, right? 12 minus 6 is 6. Okay, but there is some, if you notice this is bigger than 12, some carbon atoms are carbon-13. They have 7 neutrons, or carbon-14, 8 neutrons. Okay, there's also carbon-11 and a couple other carbon isotopes that lower it, but most of it is 12 or higher. Okay, so hopefully that's making sense. It's to explain why these numbers, these atomic masses, are a decimal and not an integer. Okay, so let's go through it, just see an example of this. Okay, so if you're doing a individual isotope, right, it's very easy because it's an integer too, right? If I have lithium-7, lithium has 3 protons, 7 minus 3 is 4. Lithium-7 has 4 neutrons. It has a mass of 7. Okay, easy. Okay, lithium-8, a mass of 8. It has 5 neutrons, 3 protons, right? 5 plus 3 is 8. Okay, those are easy. When you do the relative abundance, that is where this idea of a weighted average comes into play. And a weighted average is an average. You say, oh, averages are easy. Add them up, divide by the number. The difference is a weighted average takes into account the percentage of all the atoms that we've ever found, basically, if that makes sense. What percentage are a particular isotope? Okay, if I have, 3 isotopes. Let's say it's hydrogen 1, hydrogen 2, hydrogen 3. If you take that and just do an average, 1 plus 2 plus 3 is 6, right? And divide by 3, you get 2. You say the average mass of hydrogen is 2. And that's wrong because it's not weighted. If it's a weighted average, you would say hydrogen 1 is like 99 point, like it's crazy, 99.7% of all hydrogen is hydrogen 1, okay? Which means the mass should be very close to 1. Okay, as a matter of fact, the mass of hydrogen, if I remember correctly, is like 1.008. Let's see if I'm right. Hey, look at that. That's good. 1.008. Because almost all the hydrogen is hydrogen 1. There's a little percentage, it's like 0.2% or something crazy small, that is hydrogen 2, which means the average mass is a little bit higher than 1. Okay, there's also a very, 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 very tiny amount of hydrogen that is hydrogen 3. Okay, very small. I mean, you're talking at that point like 0.001 or whatever. It's very, very small. Okay, so the average mass of hydrogen is very close to 1.008. Okay, how do you do this? How do you do a weighted average? And by the way, I'm going through these quickly because you can always pause this and go through it, right? Is this process where you first have to figure out what the percentages are, and this will be given to you. Okay, there are problems I can do where I change it around and might ask you like, oh, what percentage is this or something like that. But I'm just going through the basic steps right now, so don't panic. Okay, what we're looking at here then is iron. Okay, iron has 4 isotopes that are common. All right, we have iron 54, 56, 57, 58. You can probably guess that because 91% roughly of iron, almost 92% of iron is iron 56, that is what the average mass is very close to. The mass of iron on the periodic table is like 55.97 or something like that. 55.845, right? So very close to 56, okay? And the reason, of course, is because, hey, almost 92% of it is iron 56, right? This basically means if I had 100 atoms, almost 92 of them would be iron 56. That's obviously the most common one, okay? We have iron 54, about almost 6% are that, right? We have some iron 57, about 2%, and then, of course, iron 58, less than 1%, okay? You might notice that it's not just 54, 55, 56, 57, right? We have 56, 57, 58, but then no 55. And you might say, why is that? It's a good question. The answer is neutrons, if we recall, are like the glue that keeps the nucleus together. The nucleus has protons together, and the protons really don't want to be near each other, okay? I don't want to get too messy. There's this very strong force called the strong nuclear force, not very creative name, that keeps protons together, but that's not the only thing happening. Okay, you also have neutrons hanging out that are basically, I'm saying basically, so don't like, please, if you're a physicist, don't kick my door down and kill me because of this, basically are glue that keep the nucleus together. Okay, the problem with the glue is too much glue is a mess and it makes the whole thing fall apart. So too many neutrons is bad, and then of course taking neutrons off is bad too. Not enough glue, the thing breaks apart. Okay, that's a good analogy. I think even an ardent physicist is going to say, okay, I get you. I know what you mean. Okay? Hopefully they're not going to come after me with their LHC. Put me in a Large Hadron Collider and see how I fare in there. That'll be the punishment for that. Anyway, where am I at? Iron 55 is basically not going to exist. It's the ratio of the protons to the neutrons is not a good ratio, and the nucleus is not going to hang around. It's going to split up into smaller elements. It'll undergo what's called decay. Okay? You've heard of radiation. You've heard of like a nuclear bomb. You've heard of nuclear power plants. You've heard of radioactive materials. Basically, it's nuclei is the plural, that are basically breaking up into smaller elements. Okay, and they release energy when they do that. That's why we use it either for, hopefully not for bombs, hopefully for nuclear power, right? But the idea is that the nucleus, right, when it breaks apart, makes smaller elements. Okay, we'll talk about that when we get to fission and fusion. Okay. So you want to know the calculation, right? So what we do first is we take the percentages, which I would give you. I don't expect you to memorize these. I would give you percentages for a given element, and you would then convert those into decimals. Okay? How do you do that? A percent means per 100. So if you take a percent and divide by 100, you've converted it to a decimal. Okay? So, for example, like I think I give you the examples I give you here, 57.076% as a decimal, when you divide by 100, would turn into 0.57076. Okay, that's the decimal percent, if that makes sense. Okay, half, right? 50% would be 0.5. A quarter would be 0.25. Think of this as like when you have cents. Like you have quarters in your pocket, right? You would say $0.25 because it's a quarter. It's 25%, right? 25 cents, $0.25. That's how you should think about this, okay? 100 pennies, right? That's 100.01s. That is 1. That's $1, right? That's percent to decimal percent. Okay, so 0.25%, now we have a percent smaller than 1, would be 0.0025. Okay, very small percentage. Okay, As you can imagine, these numbers add up to 1. Okay, percentages add up to 100, right? Decimal percents add up to 1. Gives me the decimal place over 2. That's all it is. Okay, all I got to do is take these percentages, divide by 100, get my decimal percent, and then I multiply that decimal percent by the mass of that isotope. So in the case of this, 5.845%, divide by 100, 0.05845 times the mass. In this case, 54. Iron 54 has a mass of 54. Okay. I then add these all together. Okay. And this will give me what's called the weighted average. Again, if you just did 54 plus 56 plus 57 plus 58 divided by 4, you're going to get the wrong answer. It's going to be wrong. Okay. You might say it's close. You might say, oh, come on. No, you got to get this number. You have to know how to do this. It's a skill, and it'll help you in other classes as well. It's not just for chemistry. Okay, learning weighted percentages, weighted averages is useful. Okay, so I get that number, in this case, 55.91. Okay, I think these numbers I got, I think I'm leaving out one isotope or whatever. That's why it doesn't match the P table one. Okay, but yeah, in this case, a mass of 55.910 AMUs, atomic mass units. Okay, so this is the steps, and hopefully you're saying, oh, that's not that bad. Okay, it really isn't that bad, so hopefully you'd agree with me. All right, so we'll leave it there and have a great rest of your day.